Okay, good evening, all of you. My name is Anil Yadav, and today I am here to take the seventh tutorial on fundamentals of semiconductor devices. So today we will start MOSCAP, so which is the building block of the MOSFETs, or and which is again the building block of the each and every semiconductor devices. Okay. So now, what is basically the MOSCAP is? MOSCAP is metal. MOSCAP stands for metal. Okay, here. MOSCAP stands for this is a metal oxide semiconductor capacitor. So, why it is different from the capacitor that we use? So in this in a parallel plate capacitor, how the parallel plate capacitor looks like is these are the two metal plates, and as we apply a voltage across these two metal plates, and this is a dielectric medium in between them. So this is a metal plate, this is a metal plate. There is plus q charge, there is minus q charge, and this is kind of a parallel plate capacitor. Okay. So and in this one, how these are the characteristics of the of MOSCAP, metal oxide semiconductor capacitor. This is for p-type substrate. Then when we take the p-type substrate, and this is for when we take the n-type substrate. Okay, so this is for the n-type substrate. So there are some regions which are defined. So how these characteristics are in this region. All the characteristics are same, but like if it is this LF stands for the low frequency. Okay, and capacitance with the low frequency, capacitance with high frequency. What is this low frequency, high frequency, and this is the deep depletion region? So how these are behaving? Okay, so now what we will see is, so these are the simple characteristics. I haven't told what is a MOSCAP looks like. So I will tell you about these are about the MOSCAP. How do we measure these CV characteristics? Okay. So now what we will see, this is just to show you how CV characteristics looks like. Okay. So this is the device structure, MOSCAP device structure. So this is metal, then insulator, which is the oxide. Okay, and this is the semiconductor. Semiconductor is nothing, which is our silicon. Okay, this can be n-type or p-type. Okay, this can be n-type or p-type. So here this is the this is metal, then oxide, then semiconductor. This forms a capacitor. Metal oxide, which is the dielectric layer, and this is the semiconductor. This is the structure for the MOSCAP. Capacitor. Okay, this is the MOS capacitor, and this is the from the semiconductor, the back side of the semiconductor, we have taken another contact just to so how do we take the contact? Where we put the battery? Okay, so how we take the connections, how we measure the device is from at this voltage, this we put the battery. Okay, so this is the ohmic contact on the back side of the semiconductor. So this behaves, how we apply this, we vary this voltage. Okay, this can be positive, this can be negative. Okay, so that depends on the how that we will see in the Venn diagram and in the upcoming slides, how it will behave when we apply a positive voltage at metal, and when we apply negative voltage at the metal. Okay, so that also depends on the type of the semiconductor. So here in this figure, figure, this is the Venn diagram of the metal oxide semiconductor junction. Okay, this is the metal, this is the Fermi level of the metal, this is the work function, this is the work function of the metal Q phi m. Okay, and this is the dielectric layer of thickness D, and this is the semiconductor. This part is the semiconductor. We have shown in the spatial form, spatially how it is. This is the metal. If we keep this, if we rotate it 90-degree, how it will look like? This is the metal, this is the semiconductor, no, this is the oxide layer, this is the semiconductor. Okay, in this one, as this Fermi level, as you can see, this Fermi level is closer to the conduction band. The gap between the Fermi level and the conduction band is lesser than the gap between the Fermi level and the valency band. Okay, or in other words, we can say the Fermi level is in the upper half of the band. Okay, of the band gap. So this is the N-type semiconductor. Okay, and in this one, this is for the P-type semiconductor. As this semiconductor, this Fermi level is in the bottom half, is near to the valency band. So this is the P-type semiconductor. Okay, so initially what happens is the Fermi level should match. Okay, initially when so here what we have taken is this is the work function of the metal, and this is the work function, or we can say this is the work function of the metal, and this is the work function of the semiconductor. Okay, so yes, so at this point, both the Fermi levels are matching. Okay, both the Fermi, when we join the metal, insulator and semiconductor, so the Fermi level should match. Okay, at this point the Fermi level is matching, which is the equilibrium state. Okay, equilibrium. So at equilibrium, the Fermi level should be matching with these. The Fermi level of the semiconductor and Fermi level of the metal should be at the same position. Okay, and in this one also it is at the same position. So we have chosen, in this one we have chosen the metal. In this case, the metal we have chosen this Q phi m is matching with the P-type, with the N-type semiconductor, work function of the N-type semiconductor. In this one we have chosen the metal such that its work function is equal to the P-type semiconductor. That this depends on the work function of the semiconductor depends on the doping level. Okay, how this EF will move up and down, that will depend on the doping part. Okay, so we have initially so there won't be any bending in the bands. Okay, at equilibrium, because there is the work function of both the metals and the semiconductor are matching. So we are assuming that the work function is matching in this case. So whatever we will talk about in this lecture, we will talk about we will take the P-type semiconductor. Okay, the same thing applies for the N-type, just analytically you can see that. Okay, so let me check if there is someone someone wants to join the meeting. Okay, let me check once in the call. Oh, no one. Okay, so now what we can see now, as we apply the positive voltage, negative voltage, how this metal semiconductor, this bands will behave with the application of positive and negative voltages at the metal. Okay, so what if we apply a positive voltage at this point, if we apply a positive volt, as it is an N-type semiconductor. Okay, if we apply a positive voltage, and this is okay, okay, let us just talk about not this part, let us just talk about the p type semiconductor, because the subsequent slides are for the p type semiconductor only. Okay, so just assume that initially just okay, it's initially it's in accumulation regime. Okay, so just let us say initially what we apply a negative voltage at the metal junction. Okay, if we apply the negative potential, what will happen is, so it will raise the Fermi this work function of the metal. Okay, this band will go up and this will go down. Okay, or we can say it will, if we this will go down. Yes, yes. No. Okay, so if we apply the negative voltage, what will happen is, so the electrons, the holes in the semiconductor, the positive holes in the semiconductor will be attracted towards the junction, towards the at this junction. Okay, so holes, there will be accumulation of the holes, because it is a p type semiconductor. There is an abundance of the holes are at the majority charges, majority carriers. Okay, holes are majority carriers, so is abundance of holes in the semiconductor, so holes will be attracted, a lot of holes will be attracted, and they will, a sheet of the charges of the holes will be at this junction. So there will be too much of holes at the junction. Okay, so the as we can see, so the bands at this junction, how they will behave is, so the bands will move like there will be less number of electrons, holes will be more. So this Fermi level at this junction will be more closer to the EV, but Fermi level. Okay, so this EV, the bands will move such that like this. So at this junction the bands will move up. Okay, so what we can see, at this junction when V is negative, the bands will move up. Okay, because holes from the semiconductor are accumulated at this position, so the Fermi level, the distance between the gap between the Fermi level and the valency band will decrease. Okay, because of the holes are attracted towards the junction. Okay, so bands will move like this. So as we increase the negative voltage, the bending of the bands will be more and more and more. Okay, so and then what will happen is, if we apply a very less amount of the positive charge, so it will decrease the energy level, or electron energy in the metal. So, or we can say the work function, so it will move the Fermi level down. Okay, it will move the Fermi level down, and the gap between this Fermi, the initial Fermi level and this Fermi level, so it will be equal to the applied voltage. Okay, the voltage that we are applying. Okay, so it will be equal to that. So if we apply a positive voltage at this junction, so what will happen, it will repel the holes at the junction. Okay, it will repel the holes. Okay, so the holes for majority carriers. Okay, so as we apply the positive at this junction, so this Fermi level will go down, and the holes at this junction will be repelled. So at this junction there will be a scarcity of the holes. Okay, so what will happen is, the holes are moving farther and farther, and so the holes are depleting. Okay, this is as we apply the positive voltage, so it is depleting the charge carriers at the junction, because it is now what is happening is, okay, Na minus Na and E plus. Okay, yeah, so let us say there is Na charge. Na is the charge. Okay, just a minute, let me check. Okay, so now, so as we apply the positive voltage at this junction, so what will happen is, so it will repel the holes from the junction. Okay, it will repel the holes, and there will be it is depleting the majority charge carriers at this junction. Okay, so the dopants which this is a p-type doped, so Na plus ions will be there. Okay, it is depleting the charge carriers from here, so bent holes, so it is depleting the charge carriers, and holes are moving far from the junction. Okay, so the bands will move downwards in this case, because the Fermi the gap between the Fermi level and the and this valency band, valency band, the Fermi level and the valency level, so this will increase because of the scarcity of the holes at this junction. Okay, so it is depleting the charge carriers. So as we increase the voltage, more and more holes will be more, and it will more and more holes will be repelled. Okay, so it is the depletion region width will increase as we increase the voltage. Okay, so as bands are moving downwards in this case, so there will be there are electrons. Okay, the electrons as this or we can say the gap between the Fermi level and the conduction band is decreasing. Okay, is decreasing. So what it indicates is, so the concentration of the electrons is increasing at the junction. Okay, so this is the case when we are applying. So this is for the p-type case, and the same happens for the n-type. So initially, if we this is the inversion. So inversion happens when we have the p-type material, and the electron concentration is more than the hole concentration. Okay, electron concentration is okay, minority carrier concentration is more than the majority carrier concentration at this junction, because this Fermi level is more closer to the conduction band. Okay, so therefore N is greater than P at the junction. So this is the inversion. Okay, this is the inversion. So there will be a case that will come when the inversion starts. Inversion starts at the junction when there is this point, the EI is equal to EF at the interface. Okay, EI is equal to EF. EI is equal to EF. At that point, inversion starts taking place. Okay, so so this is the starting of the inversion. So there is a weak inversion case. Weak inversion will be till then when, so okay, that we will see in the next slide. So the same thing will happen in the n-type for the n-type semiconductor. In the n-type semiconductor, when we apply a negative voltage, when we apply a positive voltage at this junction, so electrons are accumulated at this junction. So this is in the accumulation region. Accumulation. So when V is greater than 0 for n-type. Okay, and if we increase the voltage for V, okay, if we decrease the voltage, V is less than 0. In this case, the electrons are repelled from the junction. Okay, from the junction. So it is going in the depletion region. First depletion, and then as we increase the voltage more and more negative towards the negative, so this comes in the inversion. Inversion case. Okay, the same thing that we have seen for the p-type just the voltage, the voltage is in the opposite direction. Okay, so there are some terminologies that we will see in subsequent slides. There are something different terminologies are also used that I will tell at the same time. Okay, so okay, this phi s, okay, the gap between the Fermi level, the intrinsic Fermi level and the Fermi level. Okay, the gap between the Fermi level, this is the q phi bp, q psi bp. Okay, and the gap at any point between the or we can say uh, this difference from the ei, the initial ei, to the band bending. Okay, to the band bending, the ei at infinity or deeper in the semiconductor, ei in the deeper in the semiconductor, and at the interface where the band bending starts, the difference between that is the q psi pi, psi px, or because it is varying with the distance x. Okay, so it is varying, and at the junction, at the junction the gap is q psi s, or we can say at the surface. Okay, at the surface it is the interface of the insulator and the semiconductor. So this gap is q psi s, and this wd is the depletion region width that we have already seen in the in pn junction and that metal semiconductor junction. Okay, so this psi s, this psi s, there will be band bending in upward band bending, downward bending, and what is the extent of the band bending, that will decide whether it is in accumulation region or in flat band condition or depletion region or inversion, or that we will see. Okay, so so okay, let us see this one. So this is the Fermi level, this is the Fermi level ef. Okay, when we for this is the p type semiconductor, as the Fermi level is in the bottom half. So when we apply a positive charge, positive voltage at this metal junction, okay, so what will happen is the bands will move, bands will bend like this. Okay, so there, so there was a intrinsic Fermi level ei, this is ei. Okay, so if this q psi s, okay, this is the q psi s, this gap. Okay, this gap is psi s. Psi s is the, this is the potential, q psi s is the potential, or psi s is the voltage that we have applied. Okay, this is approximately equal to that one only. So this gap, if this is above the Fermi level, okay, so this ei at the interface is above the Fermi level, or we can say this is the phi bp. Okay, this is phi bp, psi bp. This is above the Fermi level, then this is in the depletion region. Okay, this depletion region. Okay, which is less than this psi bp. Psi bp is the maximum, and then it is in between, psi s is in between psi bp and psi bp and 0. Okay, this is the 0 condition, this is the 0 condition, and in between, if it is there, then this is the depletion region case, depletion. Okay, and if this psi s is negative, or this psi s is above this thing, the above, okay, then this is in the accumulation region, because as we apply the negative voltage, what will happen is holes will be attracted this direction, and these bands will move upward. If this is negative, then this is the psi s, which is the surface potential. Okay, interface, the potential at the interface is negative, less than 0, then it is in the accumulation region, accumulation region. Okay, so and So and another thing is, so if this is the Fermi level EF, and okay, this is EI. So EF, my this is psi BP. Okay, this is psi BP, and the gap between the psi BP and psi S, this is 0. Okay, the psi S is equal to 0. There is no bending. It shows there is no bending. Okay, no bending means the bands are flat. The bands are flat. This is the flat band condition. Okay, if the voltage, or in this case we have assumed that metal work function and the semiconductor work function both are equal, so there won't be any difference. So there won't be any difference at the equilibrium. Okay, so when we join the semiconductor metal and oxide, okay, so there is no bending, so this is the flat band condition. But this is not in the reality, because there is always a work function difference between the metal and the semiconductor. So that we will see how it will behave when there will be a gap between the metal work function and the semiconductor work function, and that we have already seen in the metal semiconductor junction also. Okay, how the bands will move when metal and semiconductor is joined together. Okay, so the Fermi level at equilibrium, the Fermi level should be constant, should be flat. So bands will move such that it equilibrates the charge, and charge carriers will be moved from semiconductor to metal, or metal to the semiconductor. Okay, in that case. And next case comes when this Fermi level, this is the EI, and when we apply positive voltage at this junction, positive voltage at metal junction, metal part, so as this Fermi level is moving downward, as the bands are bending downwards at the junction, so there will be a point when the EI is equal to EF at the junction. So this is the case when psi S is equal to psi BP. Okay, so this psi S is equal to psi BP. At this point, the electron concentration is equal to the hole concentration at this point. Okay, at this point, at the interface, electron concentration is equal to the hole concentration. So this is the point when okay, this is the point when the inversion starts, because after a very small positive voltage we apply at this junction at the metal part, so this will move further downwards. Okay, this will move further downwards. So then what will happen is N will be greater than P. Minority carrier concentration will be greater than the majority carrier concentration at the interface. So there is the inversion. Okay, inversion. Okay, so this is the in inversion there are two cases. Okay, there are two cases. One is the weak inversion, one is the strong inversion. So whatever we have seen, so if we apply after this one, okay, this is the EF, this is the EI, this is EI, and the gap between these two is psi BP. This is the psi F, psi S. Okay, so if we apply more positive voltage at metal junction, this is the metal junction, so what will happen is, so this band will move further, so this will move further and further, so this gap is also equal to psi BP. Okay, the band bending at the interface is equal to 2 psi BP, we can say. Okay, psi S is equal to twice of psi BP. which is in the bulk, okay, is equal to the, so the electron concentration at n at the interface is equal to twice of the whole concentration. Now n is equal to whole concentration, okay, n is equal to, okay, n, we can say this is the at the interface n p naught, okay, this is the p naught, p bulk, pb we can say, okay, whatever you can just, what I am saying is the whole concentration in a when it was not joined together, or the whole concentration is in the bulk is equal to the electron concentration at the interface, okay, when we apply a positive bias, positive voltage. So here this is the case of the strong inversion. After this, whatever we voltage we apply, that comes in the strong inversion, okay. So in this, when in the strong inversion case, what happens is, so this is what I am saying, this q psi s is equal to, this psi s is equal to twice of psi bp, okay, this is the case, okay. So whatever the voltage we are applying here, positive voltage we are applying here, which is equal to v, okay, we are applying over, hello, yes, okay. So whatever voltage we are applying here, where it is dropping in the insulator case, in the insulator, we are applying the voltage in between these two. Here is the ohmic contact that I have shown you. Here is the ohmic contact. We are applying the voltage in at these two junctions, this and this, okay. So so how the voltage is dropping in this case, as there is no, the bands are flat here, so there is no voltage drop in this region, okay, no voltage drop, because there is no field in this region, so there is no voltage drop in this region, as bands are bending here and there is band in this band, okay. This is the conduction band of the insulator, or the dielectric, the valency band is deeper, okay. So and the band is bending like this. So what is happening is, the voltage part of the voltage is dropping in the insulator, in the oxide, and other part of the voltage is dropping in the semiconductor, okay. So this vi is the voltage dropped in the semiconductor, and psi s the voltage dropping at the in the semiconductor. How much the voltage is dropping, how much the band is bending, okay. So the voltage applied is equal to the band bending, okay. This is the band bending, so this much of the voltage psi s, which is equal to the psi s, or the band bending at the interface or the surface, is the psi s, okay. So this much voltage is dropping, so the total voltage drop in the is equal to the insulator plus the semiconductor, okay. This psi s is the voltage drop in the semiconductor, and this is in the insulator. Wait. Okay. So okay, so so what we where were we? So here when we apply a positive voltage here, so how voltage is dropping? Voltage is dropping at the insulator and at the semiconductor. So voltage dropped at the insulator is vi, and voltage drop in the semiconductor, which is equal to the band bending at the semiconductor interface, insulator semiconductor interface, which is psi s, okay. So as this is a parallel plate capacitor, so this is the metal, this is the insulator, and there is a charges at this interface, how this is the, okay. So this is kind of a capacitor, which is this is, there is a charge at this interface because this is metal, and and the charges accumulate at the interface, accumulate at the surface. So there is a lot of charges at the, which we can assume it is a parallel plate capacitor kind of thing. So the charges are at this interface, and in semiconductor there are charges at the interface as well as the immobile ions in the bulk here, not in the depletion region. Okay, so the charge profile is kind of this. So there are two types of charges which are at the interface here. Total charge QS in the semiconductor is at the interface, which is because of the inversion of the charge carrier inversion as we apply the positive voltage at this junction. And another is because of the, this is the QNA, which is because of the immobile ions in the depletion region. Okay, the total charge is Qn plus Qna. Okay, so the voltage drop is equal to the, what we can say, okay, in Q is equal to CV. Okay, as you have seen, Q is equal to CV in a capacitor, so voltage is equal to Q by C. Okay, so in, and that is equal to the charge in the metal, which is the equal charge at the metal will be equal to the whatever charge is in the semiconductor, because the total charge should be balanced. The positive charge at the metal will be equal to the negative charge at the in the semiconductor at this interface. So whatever it is deeper or it is the interface, the total charge should be same. So Qm should be equal to minus of Qs. Qm should be equal to minus of Qs, and Qs is equal to minus of Qna plus minus okay, this Qs is equal to minus Qna Qn, okay, plus minus of Qna. Okay, this is the total charge in the semiconductor, and the equivalent charge is there at the metal interface. So the voltage drop because of this capacitor, because of the insulator, which is Vi, which is equal to Qs by this Ci. Ci is nothing but the capacitance of the insulator. Okay, Qs divided by Ci. Okay, so this is the voltage dropped because of the insulator. Okay, this is Qs divided by Ci. So okay, and the phi and in at the metal interface it is, and this interface, insulator semiconductor interface, is psi s. So in the next section, okay, next section I haven't shown. So okay, so total voltage drop V is equal to, okay, just replace this with this one. Okay, so a more rigorous derivation we will do in the next slides. So how much is the, so there are some formulas that you need to remember to solve the junction, to solve the for this CV whatever we can get from the CV measurements, and then we deduce. So what is the band, how much is the band bending, how much is the doping concentration and all. So from that we for that purpose we do the CV measurements. Okay, so a CV measurement. Okay, so here first I need to show you one thing. Okay, so these are the two capacitors that you can see. These are the two capacitors which are in series. Okay, yes, which are in series combination, and which is okay. So there is an oxide capacitor, COX, and there is an CS, we can say, or CD, which is because of the depletion region. Okay, there are two types of capacitors. So one is because of the oxide layer, one is because of the semiconductor depletion region. Okay, there are because of that there are two capacitors which are joined back to back. Okay, which are joined because this is one capacitor, this is second capacitor, this is COX, and this is CD, we can say. And how these are the total capacitance C can be written as total capacitance can be written as, okay, the total capacitance C, 1 by C is equal to 1 by COX plus 1 by CD. Okay, from here what we can see is C 1 by C is equal to CD plus COX divided by COX into CD. Okay, so this is the thing. And now COX by C, okay, or C by COX, okay, or COX, here we have assumed this is CI, it is written, or C instead of COX you can write CI also. Okay, so from there what you will get is C, okay, C by COX is equal to CD divided by CD plus COX. Okay, so from here if you will divide this up and by CD, so C by COX is equal to 1 over 1 plus COX divided by CD. This is the thing that we are plotting. Okay, C by CI is equal to 1 over 1 plus COX by, or CI by CD. This is what we are plotting here. Okay, C by CI. Okay, this is what we are plotting here. So initially as we are applying the negative bias, okay, initially if we are applying a negative bias, so what will happen is, so there is no, okay, initially in this region, let us say in this region, why it is coming almost equal to 1, because initially when we apply the negative bias, negative voltage, so there is a majority of the holes in this junction in the semiconductor, so there will be accumulation of the holes, so accumulation of hole at this interface, so it will be completely equal to the parallel plate capacitor. Okay, it will be completely the parallel plate capacitor. Okay, so there it is blocking the field at this junction only, so the whole capacitance is because of the insulator capacitance, so there is no capacitance because of the semiconductor, so there is no depletion region capacitance. Okay, so the contribution from the depletion capacitance is negligible. Okay, so therefore velocity is coming from this point only. And okay, just a minute. So, and as we apply, as we start, as this is the case of the flat band. Flat band in the sense, no, we have taken metal work function phi m is equal to phi s. Okay, metal work function or phi ms is equal to 0. The difference between the metal work function and the semiconductor work function is 0. The flat band condition will be at 0. Okay, the flat band condition will be at 0 voltage. So as we start applying the field, okay, as we start applying the positive voltage at this junction, so what will happen is, so it will reduce the hole concentration here because it will repel the holes here. So there will be a contribution from the from semiconductor also. And as we can see there, okay, so as we can see here, 1 by C is equal to 1 by C I or C ox plus 1 by C S big or C D, whatever you write. Okay, so there is a contribution from this one also. Okay, as and this is also, this is reducing actually. Yeah, okay, yeah, actually there is a contribution from this one also, and which is dependent on the epsilon s divided by wd. Okay, this is epsilon s divided by wd. Yeah, actually I am a bit confused, so how to tell you this thing. Initially I need to tell you how we are measuring this first. Okay, so initially what we do is we apply a positive voltage, we apply a DC voltage at this junction in between these two junctions. Okay, a DC voltage in between two junctions, and then there is a superimposition of a small sinusoidal signal, and this is what we see. Okay, this is what we see. This sinusoidal, how the charges at this junction are behaving because of this sinusoidal work. This is what we are plotting here. Okay, this is what we are plotting here. In the accumulation region, there is no contribution from the bulk of the semiconductor, because the whole capacitance is because of this. So this is equal to 1 Ci by C by Ci. Total capacitance is equal to the oxide capacitance. Okay, and so, and there are three different regions in the, okay, one is the depletion region, one is the weak inversion region, one is the strong inversion region. Okay, so the minimum capacitance is when, first I need to show you the one of the things. Okay, so here we can see, so as we apply this small signal over the DC voltage, there is a voltage applied across the two across metal and the semiconductor, and there is a oxide layer in between them. Okay, so at the metal interface there is a charge increasing and decreasing because of this sinusoidal wave. Okay, so, and after the inversion, okay, there is an inversion, this is the inversion charge at this junction, and this is the depletion, the immobile charges or immobile ions, the charges due to the immobile ions. Okay, so this junction, how this junction is behaving because of the sinusoidal wave, this is what we are capturing in this CV characteristics. Okay, so this voltage, this positive voltage is nothing but this DC voltage. So how we are measuring? We are measuring like at 0.5 voltage. We have applied a 0.5 voltage. At this voltage we are applying this sinusoidal wave. and then 0.6 voltage we are applying the sinusoidal wave. And how this is behaving because of this small signal, so we are taking that in the CV characteristics here. Okay, so at 0. So how this charge is at the junction at the interface of the if it is generating at the interface, this is in the accumulation region, in the not in the accumulation, in the strong inversion region, because there is charge at the interface also, and there is charge at the in the because of the immobile ions. Okay, so if there is charge, this is the inversion region. If we apply this voltage, this small signal with a frequency f, okay, if the frequency is too high, okay, if the frequency is too high, and this this charge or okay, another in through another thing I will tell you how it is behaving. Okay, if I am applying this is the voltage. Okay, this is the voltage that we have already applied. This is the positive voltage, the DC voltage. Okay, because of that DC voltage it is here, and above that we are applying a voltage V sine of something, sine of omega t. Okay, so at this junction, so it is going up and down, a very small, which is okay, we have applied 1 volt in 1 volt of DC plus 0.1 volt of AC. Okay, 0.1 volt of AC. So this band will move up and down at this junction. So the charges will there will be the concentration of the charges will depend on the movement of this Fermi level. Okay, so the charge carrier concentration n is increasing and decreasing at the interface. This is what is shown here. Okay, this dq, because of that small signal application which we are capturing in this one. So if this dq is if the frequency, the change in the voltage is low, the frequency of the change, the frequency is low, so the charges will be created here, and charges or this is the because of the generation of the charge carriers in the depletion region. Okay, so if it is reflected at this junction, so then okay, this is the low frequency, so this is the C type case. So the most of the capacitance, the change in the capacitance is coming from the interface only. Okay, the the change in is coming at the interface only, which is the oxide capacitance, C ox or Ci. Okay, which is the Ci. Or no, actually this is not the case, this is here, because it is equal to the Ci only. This is the because of the Ci only, because okay, so it will be the case A is the low frequency case. Okay, it is the low frequency case. So, and in another case, if we are applying this small signal is the frequency of the small signal is too high, so which is greater than the generation rate of the electron hole pairs. Okay, which is greater than the generation rate in the depletion region. Okay, generation rate in the depletion region. So so the charges will be uncovered from the edge of the depletion region. Okay, so this was the maximum depletion region width that could go, but after that because the frequency is too high, so the generation cannot happen at that faster level, so the charges will be uncovered from from the width, from the depletion region H. So depletion region H, so charge, so there will be a contribution from the from the from the semiconductor. Okay, so 1 by C is equal to 1 by C ox plus 1 by CS. So the contribution is coming from this one. So if the contribution is coming from this semiconductor one, so the overall what to say, the overall capacitance will decrease. Okay, because it is the width. Okay, the C is equal to epsilon by D. Okay, the C is equal to epsilon by D. C ox is equal to epsilon naught epsilon ox divided by the width of the semiconductor, of the width of the insulator layer. Okay, but CS is equal to epsilon into not into epsilon S. Epsilon naught is the free permittivity in the free space, and S is the semiconductor, and this is WD. WD is nothing but the depletion region width. Okay, the depletion region width will come into account, so it is lesser, so it is less. Okay, so because of that only it is and it is the parallel combination, epsilon ox divided by T ox, epsilon S divided by XD. Okay, XD or XD max. XD max is when the okay, we can say the XD max, because the charges are uncovered at the maximum of the depletion region width. Okay, at the edge of the depletion region width. Okay, so these are adding parallelly, so it is reducing, the overall is reducing, so this will go to the minima. Okay, this will go to the minima. So from here what we can calculate is we can calculate the threshold voltage. We can calculate the threshold voltage, because from here when it starts the minimum, so it starts the minimum, when it will start the minimum. Okay, when it goes to the minimum, so when it will start the minimum, this is the point of the, okay, of the, here I didn't prepare, okay, okay, how much is that? Okay, this is the okay, at minimum, what is the minimum capacitance can go? Minimum capacitance go when the depletion region width is maximum. Okay, this is the maximum and this is the minimum at this point. So from this what we can calculate is, we can calculate the threshold voltage. Okay, we can calculate the maximum depletion region width from the CV graph. How much is the maximum depletion region width can be there. Okay, so and from this point, this is the strong inversion case. This is the strong inversion case at this point. From this what we can calculate the band bending. Okay, psi BP. Okay, there are some many things we can calculate from here. Okay, okay, let us from here it will be like there is a summary of the accumulation region, accumulation, depletion, and from here you will get in a better way. Okay, so as okay, in this one, so n channel will be induced when in the accumulation region. This is the p-type semiconductor. When we apply a negative voltage at this junction, so electrons will be attracted at holes will be attracted in this direction at the interface. So this is the accumulation region. So whatever the capacitance will come from this only. Okay, whatever if we apply a small signal over this negative voltage, so whatever the changes will happen will be because of this capacitance only, because of the capacitance change in the insulation capacitance. Okay, so the capacitance, there will be a constant capacitance. Capacitance of the metal plate semiconductor is constant. This is the same case. Okay, but okay, just a minute. Okay, no one is there. Yes. Okay. So any small signal to the gate modulates the majority holes only. Okay, which is in the accumulation near the interface. There is accumulation of the holes at the interface only. Okay, so the accumulation of holes, whatever the charge is at this position, the minus qm, plus qm, or minus qm, whatever, minus qm, the same charge will be plus qs will be there. Plus qs because we are applying the negative voltage, because of that only. Okay, so there is a sheet of charges at this junction, there is a sheet of charges at this junction. So this is nothing but a metal semiconductor metal kind of junction. Okay, so this won't vary with the frequency of the semiconductor, of the small signal. Okay, so that's why this is the region of the accumulation region. Okay, accumulation region. Okay. So after this point, when we start applying the negative voltage, which is the DC bias. We have biased this in the negative direction. Okay, that we will see here. So when we apply a small VDC is equal to negative. Okay, and after that we are applying VAC we are superimposing these two. VAC is equal to, let us say, 0.1 sinusoidal sine of omega t. Okay, so this is uncovering the charges at this edge. Okay, at the edge of the depletion region. Okay, at the edge of the depletion region. So if we look at the charge profile, how it will look like is this is the row, and this is the, okay, this, there is nothing but this is the metal oxide junction, and this is the metal. This is the minus qm at this junction, and this is the plus, this is the minus qs. This is the plus qm, not minus. This is the plus qm, this is the minus qs. Qs is nothing which is equal to q times na. Okay, qna. This, so when so this is in the depletion case only. There is no inversion. No inversion means there is no charges, no electrons at this point. There is no what we can say, there is no accumulate or no inversion of the or we can say n is less than p in this region. Okay, so that's, or this is the depletion only. This is, there are no charge carriers actually in this region, because this is it is depleting the carriers at this junction. Okay, so this is the qna. So whatever the signal, small signal we are applying, that will uncover the charges at this interface. So there was the depletion region width was WD, let us say. So how it will move is WD plus delta WD. Okay, so C S or C depletion will be equal to epsilon naught epsilon S divided by WD plus WD delta WD. So this overall is decreasing. Okay, this is the capacitance, the overall capacitance is decreasing because of the uncovering of the charges uncovering of the charges in the semiconductor. The overall capacitance is decreasing, so that's why the capacitance this is decreasing. Okay, this capacitance is decreasing in this region. Okay, after reaching to the minima is when it is the WD is the maximum. Okay, minima will come when WD is maximum. When WD is maximum at this inversion, when the inversion starts happening. Okay, at inversion. Okay, in this case when EI is equal to EF, after that or after that there is a creation of the channel, but it is not that much effective, or we can say the at the n is equal to p, n is equal to p is equal to ni at the interface when ei is equal to ef. But the channel we have seen that we can say the channel is created when this the gap okay, the psi s is equal to twice of psi bp. Okay, so the bulk concentration of the holes the surface concentration of the electron should be equal to the bulk concentration of the holes. At that time only the channel is created. Okay, so it is in the depletion region, it is going down and down because it will reach to the minima when this when this depletion region is the maximum. Okay, okay, we will come in the next inversion case at this junction. Okay, now further after this point, as further we increase the positive bias again more, we increase the positive bias more, so there is the inversion. So this is the semiconductor, so inversion is starting taking place. So the electrons are more are coming the n the concentration of the electrons is increasing at the interface. Okay, semiconductor oxide interface, this is the oxide, this is the semiconductor. At this at this junction the electron concentration is increasing. Okay, so as we apply, okay, so as we apply the VDC plus VAC. Okay, so the small signal that we apply at this junction, so where the electrons will go, so more and more electrons will come here. Okay, electron concentration, electrons will come and go, come and go, come and go. Okay, so the change in the capacitance, so the capacitance is changing because of this only. Okay, so more okay, what we can say is the contribution of the capacitance is coming from the junction only. Okay, so initially there is not that much charges, so the capacitance will start rising again. Okay, the capacitance will start rising again at it will go the contribution of the capacitance will come again from the this insulate from this oxide only. Okay, because the there is no increment in the depletion region. The depletion region is fixed now. Okay, so this so now where these charges are coming from, that we will see a bit. So okay, this is the p type electron, there are holes in the bulk p dop. Okay, AF now in there yes, so there are three cases in this case. In this one, A, B we can see later, C and D. So this small signal that we are applying, that VAC, it has a certain frequency f. Okay, if the frequency is low, if the frequency is low, okay, the band bending, this band bending, the frequency of the band bending, the electrons coming and going, coming and going, coming and going, this can be these electrons coming and going can follow the frequency. Okay, up to there will be a certain extent up to which this can follow. But if the frequency of the AC signal is too high, that this electrons coming and going cannot follow that frequency, okay, then comes to the C case. Okay, so if it is following if the frequency is low, then the case this CV graph will look like this. Okay, the CV graph will look like this. Okay, but if the frequency is too high, but it cannot follow the coming and going. The coming and going is because of the generation of the electrons in the depletion region that I already told. But if the generation rate is smaller than the frequency, the generation is not happening at all because of the frequency is too high. Okay, then what will happen is the uncovering of the charges, because the ionization can happen quickly. Okay, the ionization can happen, and where is the ionization is happening? Ionization is happening at the interface, at not at the interface, at the edge of the depletion region. Okay, so there will be covering the positive charge is increasing. We can say the negative ions are increasing and decreasing at the interface because of the or we can say depletion region width is increasing and decreasing because of the high frequency. So it will follow this C. The whatever the contribution of the capacitance is coming, the capacitance contribution is coming from the bulk of the semiconductor. Okay, the WD is increasing now. WD is greater than WD max. Okay, WD is greater than WD max. Okay, so it will be this graph. So here it is this graph. Okay, it will follow this one because the uncovering of the electrons is coming from the maximum of the this edge of the depletion region. Okay, and this is the deep depletion region case, this D graph, deep depletion we call it, deep depletion. If the frequency of this we are changing the VD. Okay, we are changing the VD. This sweep, V sweep is also fast. Okay, this sweep voltage, DC voltage sweep is also fast. Both are fast. This DC voltage sweep and that AC frequency is high. So then we go in the deep depletion region. Okay, so this is the case. So now here we comes on the minority carrier comes. So in this case, so actually this is a weird thing. So as we have taken the p-type substrate. Okay, p-type substrate, there are majority of holes in this one, but we are creating an inversion layer of the electrons by applying a positive voltage, so that we can create a channel at this junction. Okay, for the conduction. Okay, so but what is happening is so if we calculate, let us calculate the number of total number of holes in the semiconductor itself. Okay, this is p-type substrate. Total number of electrons in the p-type substrate, how we can calculate is N is equal to Ni square by Na. Okay, so total number of 1 mm cross 1 mm piece, 1 mm cross 1 mm piece of semiconductor silicon, how many holes will be there? okay, which is NdV, NaDx. Okay, so area is 1 mm square, which is the if we integrate the total with the volume, so how that will come in uh, the total number of electrons, because this is the concentration 10 raised to power 15 per centimeter cube. Okay. And the area is 1 mm square. The thickness of the wafer typically it is 500 microns. Okay, so the volume, total volume of the is 1 mm into 500 micron, 1 mm square into 500 micron. Okay, 500 micron is 500 into 10 raised to power minus 4 centimeter. This is in the, and this is nothing but the area, 10 raised to power minus 2 2 centimeter square. And this is the concentration n p electron concentration, Ni square by Na, 10 raised to power 5. So it comes 50, around 1 mm square piece of semiconductor have holes. How much holes? Only 50. Okay, but as we are applying, so this is not sufficient, but we are creating the electrons at this junction, with the concentration of 10 raised to power 15 per centimeter square, per centimeter cube. So how these, from where these electrons are coming, because we do not have that much sufficient number of electrons from the in the substrate itself. Okay, so here we are applying a positive bias, here we are applying a negative. Okay, so if someone says this battery that we have uh, put here, we have applied bias from, so battery will supply, but we are applying a negative voltage here, not a positive voltage. We are applying a positive voltage here. Okay, not an, so this battery cannot supply, definitely this battery cannot supply the holes here. So from where they are coming? We do not have sufficient holes in the semiconductor itself. Okay, but what we have seen is, if in this region what we have is NP. Okay, at equilibrium NP is equal to Ni square at equilibrium. But if, as we have seen in the generation and recombination case, and if NP is less than Ni square, what will happen? Okay, there will be generation. Okay, the holes are generated in this region. In this region there is a scarcity of both the things, and because there are the electrons are not there, which because this is the depletion region. So in depletion region NP is less than Ni square. Okay, so as we increase the voltage, so what will happen is they are generated in this region. So because of these electrons that you can see, these are the generated in the depletion region itself. Electron hole pairs are generated, holes will move this side and electrons will be here only. Okay, so there is nothing but these are generated. Battery cannot supply because of we are applying the negative potential here and positive potential here. Okay, battery cannot supply. So yes, minority carrier concentration is nowhere near to the inversion, because we are creating 10 raised to power 15 centimeter cube per centimeter cube. Okay, so which is not comparable even near to the because this is 50 only, around 50 only. Okay, so this is nowhere near to that. Now yes, that we have seen, the minority carriers are generated in the depletion region. Okay, the generation must be matched with the okay. Now what we were saying is that we have already seen the rate of generation must be matched with the voltage change. The voltage change is nothing but the frequency of the AC signal. That AC signal, VDC, this VDC plus A sine of omega t. This voltage this voltage is the frequency of this voltage, it decides which curve will be there in the CV measurements. Okay, if it is too fast, then the C will be there. The CV characteristics will be like this. If it is slow, that it matches with it is less than the generation rate of the electrons, so this will be the curve. Okay, and another thing is okay, another thing what I have told is, so there will be okay, this we are sweeping DC voltage from, say, from this minus 5 volts to minus 5 volts to plus 5 volts. Okay, we are sweeping, there will be a rate of sweeping. Okay, so if we have applied something minus 5 volts at this junction, we have applied minus 5 volts. We are staying at this point for some time. We are staying at this point, say once for 1 second. In 1 second we are applying DC, this AC signal, A sine of omega t. For 1 second we are applying this AC signal. Okay, from this AC signal we are calculating the capacitance. From this AC signal we are calculating the capacitance. Okay, this capacitance is this what we are seeing. Okay, from this AC signal, and then we move from at this point. Okay, the capacitance at this, then we move to minus 5.9, minus 4.9 volt. Okay, after 1 second we move, and for 1 second we stay there at minus 4.9, and we calculate, we again superimpose this AC signal, and we calculate the again at this point, at this point, if we this time, this is the sweep rate. Okay, this is the sweep rate. 1 second we are staying at a constant VDC voltage, and then we are moving to the next voltage, if this sweep rate we are reducing, I have reduced it to from 1 second to 0.5 second, 0.5 second. Okay, I am measuring, so in this region it will be measured easily because there is no generation happening. Okay, there is no generation happening because this is the majority carriers are accumulating at the interface. Okay, majority carriers, there is no generation, but holes are moving at the interface, leaving, coming, going, that can happen easily, but there is a limit for the generation in this region. Okay, so if this sweep rate is, we are reducing 0.5 to then seconds, then to what say 0.1 second, then 0.01 second, if we have reduced to, the time is very less, we are not giving any time to calculate. Okay, I want to calculate. So what will happen is maybe okay, deep depletion region. Okay, so it is there was okay, what I can show you is, in this case, in the deep depletion region case, so we already have the depletion region width this much. Okay, so this is already depleted, and in the in the very frequent 0.01 second, again we have after this 0.01 seconds, it didn't come to the equilibrium. It didn't come to the equilibrium, but we have applied the another voltage and another say it was 4.9 okay, 3.5 voltage initially, and we have applied 3.6 voltage in very less gap. Okay, it didn't come to the equilibrium, it didn't come to this equilibrium position. Okay, but we have already applied the next voltage, so it will uncover initially here, फिर here, फिर here, फिर here. The WD is increasing. WD is increasing greater than it will go WD max. It will go much greater. So that's why we are going in the deep depletion region. Deep depletion region means we are going more deeper into the semiconductor. Okay, we are going more deeper into the semiconductor. So that's why we are going in this regime. Okay, in this regime. Okay, and yeah, it is shown here that case number D. It is shown here. So in metal there is abundance of the electrons or holes. Okay, there is abundance of electrons, so there is nothing there is no problem, they can move easily. But here we are not giving time to generate. Okay, and when we are not giving time to stable, or we can say not equilibrium, or to get it stabilized at WD max. Okay, we are not giving any time. So initially we have uncovered this much of the dopants. Initially we have uncovered. In the next voltage sweep, next like just 3.5 voltage we have uncovered this one. Then 3.6 voltage we have uncovered more. 3.7 volts we have uncovered more. And again if we are increasing the voltage at a very fast, this DC voltage very fast, we are uncovering more and more from the deep depletion, from the deeper of the semiconductor. Okay, so that's why this graph is coming. Okay, that's why this graph is coming, because we are increasing this XT much more. We are this is the XD max that can go here. Okay, that can go here, but here we are giving time, that in between the DC signal sweep we are giving time to get it stabilized. Okay, to get it stabilized. So the uncovering will happen at the maximum of the at the WD max. Okay, the uncovering of the electrons or holes will happen at the interface at this WD max only, or what we can say the additional DQ, the charge. Uncovering I am saying because we are from the dopants only we are taking the electrons. Okay, we are taking the holes, we can say, from the dopants only. This is what I So there are some important equations that you need to remember. So the important equations is, this is the VG, the gate voltage that we have applied. Okay, so the gate voltage is the total gate voltage applied here in this case. So where it is dropping at the oxide, in the oxide layer and in the semiconductor layer. So the oxide layer is the voltage dropping across the oxide layer is the minus QS divided by Cox, that we have already seen how it is dropping, because the total charge is QM. This QM is equal to minus QS. Okay, this minus and V is equal to Q by C. Q by C, nothing, the voltage is equal to Q by C for the parallel plate capacitor. This is nothing but the parallel plate capacitor only. Okay, so this is equal to minus Q by Qs by W Cox. Okay, and this phi s is nothing but, or we can say the psi s, the extent of the band bending at the interface. Extent of the band bending at the interface. This is the phi s. So the voltage drop across the semiconductor. Okay, across this depletion region. The depletion region, this is the band bending, and the voltage across. So this is the nothing but the voltage. Because of the voltage, this is the potential. As we already seen, this is the potential only. So this phi s is given by Q NaWd square by 2 epsilon s. This we have seen in the PN junction also. PN junction we have already calculated, and also in the metal semiconductor junction. Metal semiconductor junction, that the potential profile that we have we saw once. Okay, the potential profile, or it was with the x square. The potential is proportional to the square of the distance. Okay, the square of the distance, the potential was proportional to the square of the distance. So this is the same thing. Okay, so this psi s, this the potential drop here, this is nothing but depends on the depletion region width, and this WD square, and Na, Na is nothing but this is the doping concentration, and the this okay, this is the what to say, whatever. Okay, and this region, in this region, okay, in this region, this voltage profile that you can see here, the voltage profile will be linear. Okay, linear. This is because in the insulator band bending that you can see, this is the conduction band of the insulator. Okay, this conduction band of the insulator is nothing but linear. Okay, there is a linear because this is because of the polarization that we can see in the dielectrics. What happens, this is because of the polarization of the atoms. Okay, of the molecules, or polarization, there is an alignment or so whatever. Okay, this is because of that, and this is the linear, or the potential. This is nothing but the potential only, and the potential is the inverse of that, the minus 1 by q of the energy. Okay, minus 1 by q of the energy, and this is the linear in this region. This is nothing but potential versus x graph of this. Okay, the potential that we have applied is the constant potential that we have applied here. Okay, and after that it is negative, it is coming, and this here the potential is depends on the x square. Okay, this is parabolic in nature. So from here at this point to WD, it is parabolic in nature. Okay, it depends with x square. Okay, so this is the case. And the another thing is, this is the how much the voltage is dropped across the oxide is Vi is equal to Qn plus QNaWd by Cox, this much. Okay, so and this can be calculated from the WD max and all these things. So what we calculate is from the graph, from this graph, what we see is the minima point, this maxima point, this minima point. From this we can calculate the Vt. How much is the Vt? Vt is nothing, Vt is the Vth. Okay, so Vt is the Vth. From this is the formula. We can calculate the phi f. Okay, phi f we can calculate, and from phi f we can calculate the WD max, or this the maximum depletion region width, that we can calculate from here. Okay, and another thing is okay, VTH we know, QS. Okay, yes. Hmm. Okay, these are the actually this is in the strong inversion layer, when this phi f or phi s, sometimes we can this phi f, this difference between the Fermi level and the intrinsic Fermi level will be equal to phi f after the band bending. After the band bending, this is in the inversion. Strong inversion happens when this here the electron concentration at this interface is equal to the whole bulk concentration of the semiconductor. Okay, so these are the formulas that you need to remember, and with the combination of these formulas and this graph, you can calculate a lot of things. You can uh, yeah maximum of the maxima, w what is the maximum depletion region width and all. You can calculate a lot of things. Okay, so as we have once seen, this is the parallel combination of this C capacitance. C is equal to nothing but C ox parallel combination to CD. Okay, that you can see from here. This is the capacitance that is coming, and divided by Cox is equal to 1 over 1 plus Cox by CD, that we have already seen in the previous slide, that we have calculated already. So from here, when we put these values, C minima, C min of this, C minima, and this is the, and a Cox that we have already calculated from here. Cox we will calculate from here, because this is nothing but the Cox only. Okay, Cox we will calculate from here. C min we know, CD min we know. Okay, uh, so from here, yeah, actually we can calculate the CD min. CD uh, means the minimum depletion region capacitance. From CD min we can calculate the W max. Okay, so this is the thing. Okay, and one more thing is the flat band condition. Flat band, as we have assumed that work function of the metal and the semiconductor is equal, so we know that at zero, there the flat band condition is the at the zero voltage. Okay, so at zero voltage, when we apply a sinusoidal VDC, okay, what was it was V is equal to VDC plus VAC. Okay, so this is 0, and when we apply a AC signal, how the band is behaving at this, so that depth of the charges, till the charges are created, or this much depth, this depth in the semiconductor. Okay, this is nothing but LD. Okay, this LD is nothing but this is known as the d by length. Okay, this is the d by length, and CFB we can calculate the CFB from this formula, and this is the epsilon s by LD. Okay, epsilon s is the okay, this is the epsilon s by LD. So this is what says epsilon. Okay, the okay, epsilon s is the permittivity of the semiconductor, and from this permittivity of the semiconductor we can calculate the, we know there is a flat band at 0, or we inversely we can calculate many things. Okay, from here we can calculate the debye length and all these things. Okay, so this is the thing that I wanted to tell you. This is nothing but Cox plus CFB. Okay, CFB or CS, or what we can CS is the semiconductor, or CD or the depletion region. Okay, so these are nothing but connected in the series. So how do we add these series connection of capacitors are added like 1 by C is equal to 1 by C ox plus 1 by CD. Okay, so this is the fashion that we can add these, and from here, from this combination, we can deduce a lot of things. So what is the impact of the oxide layer on the CV characteristics? Okay, so the impact, how it will be is like, this is the 100 angstroms, or okay, 10 nanometer, 10 nanometer, 20 nanometer, 30 nanometer, 40, 50, 60, whatever. Okay, so what happens is, so less is the thickness, so C is equal to epsilon ox by D. D is the thickness. Okay, epsilon by D. So more is the capacitance, more is the control over the gate, more is the control of the gate voltage over the semiconductor. Okay, so more is the so less will be the threshold voltage. Okay, more is the control over the okay, lesser is the thickness of the so lesser will be the drop across this what V is equal to, okay, V is equal to Q by C, right? Or okay, what it was, yeah, V is equal to Q by C, but I wanted to see a different thing. Okay, or we can say Q is equal to CV. Okay, this Q is nothing but the charge generated in the this negative, if it is p type, so the charge in the channel. Okay, this is Q. Okay, lesser is the thickness, more is the generation of the we can say there is more of the control of the gate voltage over this channel. Okay, so threshold voltage will be lesser. If we increase the thickness, we are not doing nothing but increasing the threshold voltage only. Okay, this is the thing. Yeah, okay, this is the part a bit left now. So in real MOSCAP, there are, what is the thing is, there are certain other things. If there is a gap between the metal work function and this semiconductor work function, if there is a gap between the metal work function and the semiconductor, what will happen is, so initially when we join the metal, oxide and semiconductor, what will happen is, they will try to align, it will try to align at equilibrium. This will be equal at the same position, or at the same position. So if the metal work function was higher, okay, phi m is greater than phi s. Okay, what will happen is, so phi m is greater than phi s, so okay, this is greater, so it will come down, so it will attract the holes to neutralize it, to make it equal. Okay, so holes will already be there. Okay, how it will look like is, it will look like, like this. This is EF, this is EC, EV, this is EC. Okay, it will look like this. And no, this is EF, this is EI. Okay, this is the thing, this is kind of thing. So if phi s is phi m is greater than phi s, already there are holes at this position. Okay, more of the holes at the interface. So we need to apply more voltage first to make it the flat band. Okay, first we need to apply the more voltage to make it flat band like this, and then it will go in the in the in the depletion region and then in the inversion region. Okay, so it is already in the accumulation region already in the accumulation region. So in this case VTH will be more, because first we need to remove this accumulation region. To remove this accumulation region, we need to apply how much voltage? 5 ms. Okay, the difference between the metal and semiconductor work function, that much voltage we need to apply to make the bands flat initially. Okay, that much voltage we need to apply. Okay, so this much voltage we need to add 5 m minus 5 s. This much voltage we need to add here. And another thing is, there are fixed charges at the interface okay, at the metal at the interface. So here, to compensate with the fixed charges, we need to apply more voltage. They can be positive or the negative. So we need to apply more voltage, or that can be more voltage or less voltage. Okay, that will depend on the charges, q fixed charges. Okay, it is positive or negative. So this much voltage we need to apply more. Okay, this much voltage we need to apply more to make the bands flat initially and to fill the fixed charges, and this is the extra voltage for the threshold. Okay, then only we are going in the inversion region, not before that. Okay, so this is the metal work function. So this is the metal work function is lesser. Okay, in this side we are going more work function. Okay, the work function is increasing. AZ is around minus 5.1 electron volts, not AU is around minus 5.1 electron volts, and this is, I don't remember. Okay, so these are the things that you need to keep remember. Okay, if time is almost up, if you have any doubt you can ask. Okay, so this was a bit confusing, because it is a bit confusing because of these this sinusoidal, and there are things. But if you this is also easy if you understand the basic concept, basic thing behind. This is the whole thing that we are doing actually. DC voltage we are applying, and over that we are applying the AC signal. How this AC signal is uncovering the charges in the semiconductor layer. This is what is replicated in the CV measurements, and from these measurements we can find out the depletion region width, and we can find out what the things like doping concentration and all. Okay, if you are given with a semiconductor, you don't know the doping concentration. Okay, just take the CV measurements. Okay, from there you can do a lot of things. Like if you do the CV measurements, you will get this region, and do it at the low frequencies, so that you can get the C minima and you can see in which region you are. Both the both things you can do, so that you can see if it is p type or n type also. Okay, it is just flipped for the n type. Okay, if you have your substrate is n type, it will just get flipped, nothing. Okay, so hmm, hmm, yeah, if you have any doubt you can ask, otherwise you can leave. Or if you have any doubt from the any of any other lectures, or you can ask from the previous lectures. So okay.